Hello, and welcome back to CS492G, Foundation and Future of Virtual Reality, Artificial Intelligence, and Massively Multi-User Online Role-Playing Games. We are currently in Chapter 2 on Artificial Intelligence. We have already covered important foundational questions, such as the philosophy of artificial intelligence and pedagogy of artificial intelligence and history of artificial intelligence. And today we're going to look at some more technical aspects, namely one of the early theorems about artificial intelligence and about machine learning pertaining to the first such model, namely the perceptron. And this presentation will be given by Dong Sok. So here you are, and
Yes,
I'll let you share the screen and start your presentation. Thank you.
Then, hello, my name is Dong Sok So, who first index is like this. First, I will say about neuron and single layer perceptron and perceptron convergence theorem, XOR problem and multi-layer perceptron, activation function, loss function, and optimization. First, neuron is composed by soma, dendrites, axon terminal, and terminal buttons. The neuron receives signals from the dendrites and pass signals along to axon and send signals to another neuron's dendrites. So from the neuron, Frank Rosenblatt invented the perceptron in 1958. First, the perceptron gets some input values and weight. Get input value and applied weight to the input values, then it can make the output value y. If the sum of weighted if the weighted sum is larger than zeta, then output value is 1, and the weighted sum is less than zeta, then output is 0. Also, there are some bias for the perceptron. It is same as previous slide, but it has some bias for result. So we can simply add plus b at the weighted sum to make this bias. Then single layer. Yes. Who have some question? Or I will go ahead. The single layer perceptron has only 2 layers. So we code in each steps in right picture, and each step is a layer. So in single layer perceptron, it has first step for input layer and second step for output layer. And perceptron convergence theorem says perceptron completes learning at a finite time where the data is linearly separable. Linearly separable means two groups distributed in a multi-dimensional space can be divided into one hyperplane. The perceptron will find the separating hyperplane in a finite number of updates. Also, if the data is not linearly separable, it will loop forever. Then let the training set x plus and x minus is linearly separable, and training set x is the the cup of x plus and x minus. And also it has n number of data. Then let y is the label which satisfied yi is +1 or -1. Let we input the data in the following order from start to end and repeated the process. Then when the theorem said that when the output is wrong, we save input data as x1 to xn, and the initial weight is null, it is equal to 0, then, and we update the weight by the saved wrong data. Then there are some n0 which satisfies the following equations and initiation. Then it is the proof about this theorem. First, let's assume the number of wrong data is n. Since we predict xn is wrong, so wn plus 1 is wn plus yn xn. Also, we assume the x plus and x minus are linearly separable. There are some solution w star which satisfied the following inequation and equation. Then we can present w star t wn plus 1 is w star t wn plus yn w star t xn. Also t is transpose. Then let's define alpha is the mean value of y w star tx. Also, it is bigger than 0. Then we can change the last line of previous slide. We can change it to inequation. Since the initial weight W1 is 0, we can recursively apply the inequation. Then we can get we can get the first one, w star t wn plus 1 is bigger or same to n alpha. By Cauchy-Schwarz inequality, we can change the norm of wn plus 1 square is bigger or same to norm of w star t squared. Therefore, we can get the square of the norm wn plus 1 is bigger or same to n squared and alpha squared. Then we can, so let's assume the number of wrong data is n, like the previous step. Since we predict xn wrong, so I think this slide is okay. So let's define beta. Beta is max of the norm of x squared. Since wn plus is wn plus yn xn, the norm of wn plus 1 can represent it like this. Since yn transpose wn xn is smaller than 0 because we have some wrong prediction about this xn, we can change the equation to this inequation. Similarly, the w1 is 0, and we can apply the inequation recursively. We can get the square norm of wn plus 1 is n beta. So we can get a square of norm Wn plus 1 is smaller or same to n beta. So we can get, so now we get the lower bound and upper bound of Wn plus 1 square of norm Wn plus 1. We can get n squared alpha is smaller or same to n beta. So we can get the number n as upper bound, and it is equal to the max of the number n. This means that the maximum number of times the perceptron fails to predict is alpha squared alpha beta per squared alpha. After that, the prediction is successful for all training data. Then the single layer perceptron, which has two inputs, can make a line in the plane. So it can solve AND gate or not AND gate. Like these three pictures, the line can dark, false and true. But the single layer perceptron can't solve XOR gate because we can't separate XOR gate by a line in the plane. Two line or some curves. So we use multi-layer perceptron. In multi-layer perceptron, it has more than two layers. So in right picture, first step is input layer and intermediate steps are hidden layer, and last step is output layer. Input layer and output layer are fixed to the number one, only one, but we can get many intermediate steps. So deep neural network, we call DNN, has at least two hidden layers. So it is activation function which is applied to the output of the perceptron. The step function is we already used at the perceptron, but the sigmoid function is the others. Since these functions return a value in the range 0 to 1, so a gradient problem occurs in which the value becomes very small as applying activation function accumulates. For example, the sigmoid function is half of 1, so we can get 10 times, then it is very smaller, like very smaller. Also, the step function, sigmoid function, and Lalu functions are nonlinear functions. We have to use nonlinear activation function in neural network. When let the neural network with 3 layers has some activation function, fx is ax. Also, a is the real number. Then the 2 times and 3 times of the activation function, it is same to some other linear, like the f prime x is a 3 times x. So we can consider these 3 layers as this one layer. Loss function is that difference of the predict predict data and real data. If the value is small, it means that it is closer to the real data. Also, it is same to we predict the data as well. So there are some loss functions, but I will introduce these three loss functions. Is mean squared error. It is squared. It is mean squared error means the difference, the mean error and it is squared. Also, in mean absolute error is the absolute value of error, and the cross entropy is like this. We use the minus because the value is okay. Then optimization is the process for function. Gradient descent is a first-order interactive optimization algorithm for finding a local minimum of a differentiable function. And the stochastic gradient descent is applying gradient descent for some selected data. It can reduce the time of execute. Momentum is applying gradient descent, but it also uses previous gradient. Previous gradient. Gradient descent has some problems, like the first one and the second one, saddle point. Since the gradient descent uses the gradient of the function, it may occur some problems about local minimum and saddle point. Gradient descent can move to the local minimum, which is the global minimum. It is the program really want to find it, but it can stop at the local minimum. Also, instead, the gradient of the function is 0, and it stops at that point. So we can avoid these problems by using less gradient, which called momentum. I introduced at the previous slide. Then this is the reference of my presentation. Thank you.
Thank you very much. Thank you. And this is, as you may have noticed, a technical contribution, right? Usually we try to focus on the non-technical parts, but this is really about the mathematical aspects of machine learning with a rigorous definition and rigorous theorem. So this is kind of a higher level of difficulty, I'd like to say. So thank you so much for for that. And it's also one of the earliest, I think, theorems about artificial intelligence, right? Historically speaking. So just for your reference, right, I wanted to show you this here, right? So what you see here is the book where this perceptron theorem was proven. It's by Marvin Minsky. You all know Marvin Minsky, one of the early proponents of artificial intelligence. It's about perceptrons, and it's called, as you see here, An Introduction to Computational Geometry, right? Now you may know that computational geometry is one of the strong points of KAIST, right? With, for example, Professor Ottfried has written this famous textbook, and computational geometry arguably started with the development of perceptrons, right? Or is closely related to machine learning. So machine learning is not so new if you think about it. So that's one thing I wanted to point out. So I think this is from the 60s, the first edition of this book. Right. Yes, so that being said, let's now move on to the, let's first take a 3-minute break, right? To digest this. So here comes the break. So welcome back from the break. And I'd like to start by asking Dong Sok to briefly summarize some key points of his presentation, few basic messages that the audience, that you guys should remember and take home from his presentation. Could you do that?
I think the key point of today's presentation is perceptron and perceptron convergence theorem, because the other activation function or loss function, these things are we can study at the other part, maybe the convolution networks, maybe in the machine learning or deep learning. So I think the perceptron and perceptron convergence theory is the today's presentation.
Yes, so indeed. So the perceptron as a model of machine learning, right? First model, then a characterization of what this model can learn and what this model cannot learn. Namely, it can learn geometrically those decision problems, right? It's about yes and no problems. It's not about function problems. And it can learn decision problems that are linearly separable, right? So that's a very geometric characterization of what single layer perceptrons can learn and what they cannot learn. And thirdly, a theorem that the learning algorithm, right? That's one is the model of computation, and the other thing is the learning algorithm, the training method, that this training method is indeed successful and can will learn precisely those problems that are linearly separable. Eventually, there's no complexity statement. It doesn't say how fast it converges, right? But the statement says whenever the underlying problem is linearly separable, then the learning algorithm corresponding to the perceptron will eventually converge, right? And then there's a statement that XOR cannot be learned because it's not linearly separable. And finally, the generalization that we nowadays use all the time, namely multi-layer neural networks. So I think these are the 4 key points, right? And what remains open, and I think still remains open, is what can multi-layer perceptrons learn? Can they learn everything? Probably not, right? So what are things that multi-layer perceptrons cannot learn? I think such statements, the mathematical foundations of machine learning is still big open question, right? And of course, the answer will also depend on the activation function, right? Dong-Sok mentioned several activation functions that are commonly used in multi-layer perceptrons. Good. Yes. So that's a kind of summary of the talk. And now it's time for you to ask questions or to add comments. Maybe some of you have already attended lectures on machine learning and have know more about the contemporary technological side of machine learning. That would be interesting to hear about that, because frankly, I myself don't know about contemporary technological aspects. But please refrain from assessing the quality of presentation, because that will be the subject of our final part of today's session. So comments about the content and questions and additional remarks about perceptron theory. Who has taken a course on machine learning? Hands up. So thank you. What did you learn in this course?
I first heard about the perceptron convergence theorem at this time, and I'm just curious, what is fundamental difference between gradient descent algorithm usually used in optimizing neural network? Yeah, what is the fundamental difference between them?
Yongsuk, do you happen to know this?
He asked the difference of gradient descent and what? I didn't didn't.
Oh, did my mic was bad quality?
No, my internet is little bad.
Okay. I asked the difference between the gradient descent and your perceptron convergence theorem.
Gradient descent. Gradient descent is the gradient descent find the loss functions. Reduce the loss functions value, and the perceptron convergence theorem find the better perceptron which can distribute the values. So it is okay.
Yeah, I think, yeah, good, thank you.
Maybe it helps to compare with simple optimization problems, right? So suppose you have a function, right? Real function, one-dimensional function, and you want to find the maximum or root of that function, right? Then one common way of finding a root is, for example, bisection, right? You look whether the function in the middle of the interval, here's the interval, and you look whether the function here is positive or negative. And if it's positive, then you proceed to the left half interval. And if it's negative, you proceed to the right half interval. That's bisection. And then there's an advanced method, which is Newton's method, which takes into account the derivative, right? So that's a first order derivative. And Newton's method is faster if you start at a suitable starting point, right? There are all these counterexamples in classical optimization that Newton's method is very bad if you start with a bad starting point. And so what we're talking about here is kind of the multi-dimensional counterpart to that, right? So here we have higher dimensional geometry, right? So linear separability. And the gradient descent method is a high dimensional version of Newton's method. And the perceptron algorithm is a high-dimensional version of bisection, basically. So again, what between the lines, what you hear here is all these things have been studied and also taught for many decades under different names. Namely, it's just optimization, numerical optimization, now under new names like machine learning. Okay, then let's conclude here the part about the contents. And this is the time where we should all thank the speaker once again. So thank you so much. Of course, now I'm going to stop the recording.